If you've spent any time in precision manufacturing, you know that sound.
Oh, yeah.
That high-pitched, tooth-rattling squeal that just vibrates right through the floor and into your bone.
Right into your skull.
That's the sound of vibration. Chatter, and it means your very expensive, very complex part is probably about to be scrapped.
It's the universal complaint, isn't it? That sound. It's not just noise. It's the physical proof that your cutting tool is fighting a workpiece that, well, it just doesn't have the rigidity to stand up to the pressure.
And the result is immediate.
Immediate. Ruined surface finish. You have zero chance of holding tight tolerances, and you get parts coming out oval or, severely tapered.
Exactly. We're talking about a fundamental physics problem when you're turning long, slender material. But today, we are doing a deep dive into the powerful, yet I think often misunderstood, solution for this exact rigidity crisis.
The steady rest.
The steady rest. This thing is an absolute game changer, and for some jobs, it moves from being just a helpful accessory to a totally mandatory requirement.
And that's really our mission today. We want to give you a shortcut to understanding not just how to use it, but the critical rules and the quality trade-offs that are involved. This isn't just friendly advice.
Right.
It's a technical mandate. It's driven by the material itself. And we have to start with the single non-negotiable rule taken straight from the best shops in the world.
Okay, what is it?
You must use a steady rest when the length to diameter ratio, the LD ratio of your workpiece, exceeds 2.5 to 1.
2.5 to 1. That's it. That's the technical line in the sand.
It is.
If your shaft is more than 2.5 times longer than it is wide, you are officially in the danger zone. You need structural reinforcement, period.
We see so many operators, even experienced ones, who hit that ratio, and they try to manage the problem away.
Right, they try to trick it.
They try to trick it. They'll slow the spindle way down. They take these feather-like cuts. Sometimes they'll even switch to a specialized insert. All of it hoping to cheat the physics of a long, cantilevered beam.
But it's slow. It's inefficient.
And it often still results in poor quality. The steady rest gives you that essential radial support. It physically stops the long part from bending or oscillating under the constant immense pressure of the cutting tool.
So let's define this thing properly. You called it an intermediate fulcrum, which I think is the perfect term.
Yeah.
What exactly is a steady rest? And what role is it playing that, say, the chuck or the tailstock just can't handle?
At its core, it's a structural support device. That's all it is. It mounts directly to the lathe bed, and it uses 3 adjustable jaws or rollers. You can think of them as fingers, really.
Okay.
And these fingers cradle and hold the midsection of a rotating part. It's an auxiliary device, and its single crucial goal is to increase the overall stiffness of that part while you're machining.
That intermediate fulcrum concept really nails it. Instead of just holding the ends, you're adding a pillar right in the middle, stopping that flex.
You got it. It's perfect for anything long and slender, transmission shafts, long bolts, precision rods.
So when you look at the different types, it seems like the industry has really specialized these for every possible situation.
Oh, absolutely. It all depends on the production volume, the complexity, and sometimes the sheer weight of the part.
So let's unpack those. Let's start with the basics, the manual rests.
Right. Manual steady rests are your workhorse. They're often used for large batches, or when the setup is simple and you're going to do it over and over again. You set them up once, and you have to meticulously center the jaws to the true axis of rotation.
So they're great for high-volume production because you're not constantly tweaking them.
Exactly. They usually have fixed pads or rollers, sometimes made of brass or a special low-friction plastic to avoid, marring the surface.
But when you move into modern CNC work where, let's be honest, time is money and parts are incredibly complicated, a manual setup just feels like a burden.
It is, and that's where hydraulics come in. The jump to hydraulic steady rests is all about speed and repeatability. They're essential for small batches, complex parts, and especially for operations like turn milling. Instead of hand cranking 3 screws, the clamping force is applied and released instantly and evenly with hydraulics.
And that means you can do multiple operations in one setup.
That's the key. You can turn a profile, then maybe drill an internal feature, all without stopping and recalibrating the support. That alone can save hours.
And then what if we go from complex to just colossal?
Yeah.
I mean, parts that are pushing the limits of the machine itself.
Then you need the true heavy hitters. The hydrostatic steady rests. These are for massive components, things that might weigh tens of tons.
Wow.
Think about massive ship shafts or the big rolls they use in steel mills. What makes them unique is they support the workpiece on a thin film of pressurized oil.
So there's almost no friction.
Near zero friction. It's this incredibly stable non-contact support that's just unmatched for handling those extreme loads while still allowing for the fine-tuning you need for ultra-high precision.
I also saw a mention of an even more advanced type. Servo-driven rests with grating feedback. That sounds like science fiction.
It's pretty close. That's for work where coaxiality errors are absolutely not an option. Think aerospace or certain high-end mold making. The servo drives let the rest actively track and adjust its own position in real time.
That's self-correcting.
It is. It guarantees the work diameter stays perfectly concentric with the spindle axis along the entire length of the part.
Okay, that gives us a clear picture of the tools. Now let's tackle that big operational choice. When does the steady rest actually replace the tailstock? Because, I mean, the tailstock is everyone's default for supporting a long part.
It is, but the choice is really defined by the part's shape and what you need to do to its end face. Relying only on a tailstock means you're just supporting the two ends of a flexible beam.
Right.
When your tool hits the middle, that whole unsupported span just bows out. The tailstock is great for preventing movement along the axis, but it offers almost no radial support against that sideways cutting pressure.
So even if my LD is, say, just 3-to-1, why would I risk the complexity of a steady rest instead of just using my tailstock and, I don't know, taking a lighter cut?
Because of what we can call the boring problem, this is the single biggest advantage of this steady rest.
The boring problem. Okay.
If you have a long shaft and you need to do any internal work on the end drill, a hole, tap a thread, cut an internal groove, the tailstock is physically in the way. It completely blocks your access.
So you have to remove it, which means the entire shaft is now unsupported and you're right back in that chatter zone.
Precisely. The steady rest holds the shaft securely from the outside diameter, making the whole thing rigid while leaving that entire end face wide open. It's absolutely mandatory for any kind of high-precision internal work on a long part.
And beyond just access, we have to talk about pure brute force. You mentioned rough machining forces earlier. Can you put that into perspective for us?
Sure. When you're taking a really deep rough cut on a tough material like stainless steel, the radial forces can easily hit 1,000 newtons, sometimes up to 1,500.
Which is,
Yeah.
what, about 330 pounds of sideways force?
Exactly. Now imagine trying to push a flexible rod sideways with that much pressure. It's going to bend. A lot. A standard tailstock center just isn't designed to handle that kind of lateral force on a slender part.
But the steady rest is bolted right to the machine bed.
It's a solid anchor. It just absorbs that shock and that load.
There's also a safety thing with hollow parts, which I thought was fascinating.
Yes. If you push a tailstock center into the end of a hollow tube, that point creates outward pressure. If the tube wall is thin, or the material is brittle, you can actually split the end of the tube.
You can split it. Wow.
Or deform it into a bell shape. The steady rest, on the other hand, clamps the safer, more structurally sound outside diameter. It prevents that dangerous internal stress.
So access and strength both favor the steady rest. But are there ever times where you have to use the tailstock, even if the LD ratio says you shouldn't?
Yes, unfortunately. If the shaft you're turning has a lot of small steps or shoulders or grooves along its length.
There's nowhere for the rollers to sit.
Exactly. The rollers would just keep bumping into those features. You can't safely clamp it anywhere. In those cases, you're sort of forced back to using the tailstock and just accepting that you need to take lighter cuts and go slower.
Okay, let's shift to the payoff. Why do we go through all this trouble? It comes down to killing the two biggest quality problems: dimensional error and poor surface finish.
It does. And you can spend hours, debugging your G-code, changing your tool insert, messing with the spindle speed,
Okay.
when the real problem is just a total lack of support.
The steady rest is a direct fix.
It is a direct fix for two core physical issues: deflection and harmonic vibration.
Let's start with deflection, that push-away effect, because that's the #1 cause of taper error.
Think about it simply. Your cutting tool moves towards an unsupported, long shaft. The material literally flexes away from the tool pressure.
Right.
So if you programmed a 5 millimeter depth of cut, but the material bends away by, say, 0.1 millimeters, your actual cut is too shallow.
And then as the tool moves past, the material springs back.
It springs back, and that spring back is what creates the dreaded taper.
Right, because the ends are held rigidly so they're the correct diameter, but the middle is now thicker.
Precisely. You get this parabolic shape. That's a taper error. A steady rest physically prevents that spring back. It holds the part firm, ensuring the cut matches the program exactly along the entire length.
Okay, so that's deflection. Now for the other quality killer, harmonic vibration. The guitar string metaphor is pretty good here.
It's a perfect metaphor. The shaft has a natural frequency. It wants to oscillate at a certain speed. When the tool hits the part, it introduces energy that excites that frequency.
And because it's long, it acts like a vibrating string. It creates resonance.
And that resonance is the chatter you hear and those ugly wave pattern marks you see on the surface.
So the steady rest isn't just stopping the bending, it's actively damping that vibration.
Yes, it's a massive damper. By putting 3 fixed points of contact along the length, you completely change the acoustic properties of the part. You break the feedback loop that creates the resonance.
And killing that chatter lets you get a smooth, sometimes even a mirror-like finish.
A finish that would be totally impossible without that support.
And for those super high-precision jobs, like the mill rolls you mentioned, geometric accuracy is everything.
Absolutely. The steady rest is vital there because it minimizes runout, that subtle wobble of the part. By keeping the diameter perfectly concentric with the spindle axis, you ensure a consistent machining datum. That's the difference between a successful part and a failed assembly.
Okay, we've established the steady rest is mandatory for quality. But here's the big warning. It is also the quickest way to scrap an expensive part if you set it up wrong. This is the danger zone.
A bad setup is immediately destructive. I mean, you have to remember, the whole point of this tool is to make the part rotate perfectly around the spindle axis. If the steady rest itself is misaligned, well, it forces the part to rotate eccentrically. It guarantees failure.
So what's the most common, most destructive alignment error?
Center alignment. If the steady rest jaws are clamped too high or too low, even by a tiny amount relative to the true center line, the rest literally bends the shaft.
It's forcing a bend into it with every rotation.
With every single rotation.
Yeah.
And that creates eccentricity. The center of rotation shifts, and the diameter you cut will not be round. It can't be.
That sounds bad, but the sources warned about something called lobing, which sounds even worse. That's from too much clamping force.
It is, and it's different from eccentricity. Eccentricity means the center is off, but the shape might still be round. Lobing is a true geometric deformation.
Okay.
When you over-tighten those 3 jaws, you are locally deforming the metal into a 3-lobed or sort of triangular shape. The pressure points are literally forcing the metal inward.
So when the tool cuts that shape, you end up with a part that, if you measure it with a caliper, it might seem round.
It will. The diameter will measure correctly.
But it won't fit into a round hole because it's actually a polygon.
Exactly. It's a subtle but devastating error, and it leads right to the next risk, overconstraint. If you tighten the rest too aggressively, the steady rest ends up fighting the chuck.
So one is trying to hold it one way and the other is trying to twist it.
Yes, and that twisting force doesn't just cause a geometric error, it locks internal stress into the material.
And that stress can cause the part to warp or fail later on, long after it looks perfect coming off the machine. That's a scary thought.
It is. And another huge trap, especially with older manual rests, is friction and heat. Without constant proper lubrication between the pads and the part, you generate friction heat incredibly fast.
And how does that affect the dimensions?
Well, heat causes metal to expand, so the part physically swells during the cut. You might measure it and it's perfect, but the moment it cools down, it shrinks right past your tolerance.
And that's not even mentioning the damage to the surface.
Right. The friction can cause scoring or marring, where the pads just physically dig into and ruin that beautiful surface finish you were trying so hard to get.
Okay, so let's end on what might be the most critical operational rule of all. It's about timing. When do you actually engage the steady rest?
This is absolutely essential. You must never, ever clamp a steady rest directly onto a rough casting or raw forged surface.
Why not?
Because those surfaces are never perfectly round. They're naturally oval or a little stepped or just not concentric. If you clamp your jaws onto an oval shape, the steady rest will lock that oval in. Your precision cut will then just follow the contour of that initial error.
So it's a two-step process. You can't just throw it on there.
Absolutely not. You must first turn a dedicated spot. A short, true, smooth, and perfectly round surface on the shaft using just the chuck and maybe the tailstock.
And then you bring in the steady rest.
Then you bring it in and clamp it onto that perfect concentric spot. That's the only way to guarantee the rest, is holding the part true to the spindle axis for all the work that follows.
That one sequence ensures quality from the very start. Okay, so to summarize this deep dive for you, If you are turning a long part, and that means an LD ratio over 2.5 to 1, the steady rest is not optional.
It's mandatory.
It's mandatory for rigidity, for allowing that critical end-face machining the tailstock prevents, and for guaranteeing the high precision and smooth finish that the forces of machining would otherwise completely destroy.
It's the direct engineering solution to a physical limitation. It transforms weak, flexible material into a rigidly supported assembly that can withstand massive, concentrated cutting forces.
So what does this all mean for you? We spent a lot of time talking about how an improper steady rest setup, that over-constraint problem, can actually twist a shaft internally, locking in unseen stress because the rest was fighting the chuck. If a seemingly helpful support device can create those hidden stresses, that raises a pretty important question. What other unseen internal stresses, caused purely by the forces of machining, the sheer pressure of the cut itself, might be locked into your finished parts, just waiting to cause unexpected warpage or outright failure down the line? Something for you to mull or explore on your own.